All right, so looking at an example where we're going to use the superposition principle and the new shapes that we've learned. So we have a thin plastic disc with radius 3.2 meters, is uniformly charged with charge being equal to plus 8.5 times 10 to the minus 5 coulombs, is attached to a rod. Of 9.5 meters. The rod has a charge of minus 3.6 times 10 to the minus 6 coulombs, and the center of the disc and the rod are at the origin. So what this looks like is we have our, go ahead and draw a coordinate plane. This is going to be y, this is going to be z, and x is going to be coming out. Our disc is here in the x and y plane, and then our rod is going right through the middle of it, lying in x. So, and disc is in YZ. What is the electric field at location 0.07, 0.2, 0.5 meters? All right, so the solution to this is we need the superposition principle. And so the net electric field is going to be equal to the field contribution from the disc plus the field contribution from the rod. All right, and we'll calculate each of these separately. Starting with the field from the disc. So in this case, the observation is close to the disc and far from the edge, so we can use the approximation. E disc is approximately Q over A divided by 2 epsilon naught. Q is equal to 8.5 times 10 to the minus 5 coulombs. Area is pi r squared. And epsilon naught is equal to 8.85 times 10 to the minus 12 Coulomb squared over Newton meters squared. Okay, so we can plug that into our equation for the electric field. We get that the electric field is 8.5 times 10 to the minus 5 coulombs over pi times 3.2 squared over 2 times 8.85 times 10 to the minus 12 coulombs squared over Newton meters squared, approximately 1.49 times 10 to the 5th newtons per coulomb. All right, now to think about what direction this is, our disk is positively charged, and so what you're going to get is you get this field that is perpendicular to the disk that we've seen before when we were calculating the disk, and this field is going to be in X. It's going to be along the same direction as that rod, and in this case our observation location is on the right hand side of the disk, so the field from the disk is going to be in positive X. So E disk 1.49 times 10 to the 5th, 0, 0 newtons per coulomb. All right. So now that we have the field of the disk, we can then go on to the field of the rod. In this case, the observation location is close to the rod and far from the ends, so the electric field of the rod is approximately 1 over 4 pi epsilon naught, 2 Q over L over little r. R is going to be the observation location minus the source. This is equal to 0.07, 0.2, 0.5 meters. Now, with the rod lying in X, in this case, that means our X is going to be 0.07. For the source, 0 and 0, because you're just coming directly up from it. So if we look at that, so here's Y and X. So you'd be observing here, and then Z and X, and you're observing here. Okay, so R is equal to 0, 0.2, 0.5 meters. Our magnitude is equal to 0.2 squared plus 0.5 squared meters, which is 0.539 meters. Our hat is equal to 0, 0.2, 0.5 over 0.39, which is equal to 0, 0.371, 0.928. And so the electric field of the rod is 9 times 10 to the 9 Newton meters squared over Coulomb squared, 2 times minus 3.6 times 10 to the minus 6 coulombs over 9.5 meters over 0.539 meters. And so you get the scalar component of the rod is approximately minus 1.27 times 10 to the 4 newtons per coulomb. And to get the field of the rod as a vector, we need to multiply the scalar component by the vector, or the unit vector. So 0.371, 0.928, and you get the electric field of the rod is approximately 0 minus 4.71 times 10 to the 3 minus 1.18 times 10 to the 4 newtons per coulomb. And the net field, we're going to sum the two of those together. It's equal to 1.49 times 10 to the 5th, 0, 0, plus 0 minus 4.71 times 10 to the 3 minus 1.18 times 10 to the 4. And the net field, 1.49 times 10 to the 5th minus 4.71 times 10 to the 3 minus 1.18 times 10 to the 4 newtons per coulomb.